All right, so yesterday we covered the integral, or yesterday, last class we covered the integral test, which was basically this: if the integral from 1 to infinity of the function that is related to the corresponding sequence is convergent, then the series sigma an is convergent, and if that same integral is divergent, then the series an is divergent. Now, we did a couple examples of that, and we stopped with this one, so I'm going to do one more example. We're going to get one more theorem, and then I will probably let you guys go early today. So determine whether the series sigma natural log n over n converges or diverges. Remember that the conditions for the integral test are that it has to be continuous, positive, decreasing function. All right, so in this specific example, we definitely know that this is continuous and positive as long as n is greater than 1. Because if n equals 1, natural log of 1 over 1 is 0. But for any value greater than that, that's going to be a positive number. Decreasing is not necessarily obvious here. So we need to prove that it's decreasing. Before we can use our integral test. All right, so thinking back in your calculus knowledge, how can we determine if a function is increasing or decreasing? The derivative. If the derivative is positive, the original function increases. If it's negative, it decreases. So what we're going to do is look at the corresponding function, f of x equals natural log x over x, and we'll take its derivative, f prime of x. So again, we're going to reach back into Calc 1. We're going to have to use the quotient rule here. So low, which is x, d high, derivative of natural log x is 1 over x, minus high, natural log x, d low, derivative of x would be 1, divided by x squared, right? All right, so we get 1 minus natural log x over x squared. All right, let's go ahead and set that equal to 0. And we'll solve. So you can multiply both sides by x squared. We get 1 minus natural log x equals 0. Natural log x equals 1. How do I solve that? Yeah. Exponentiate both sides by e, we get x equals e. So then we can just look at our derivative on either side of e. E is basically what we call a critical value. So that's where the derivative is 0. So the derivative either needs to be positive or negative on either side of e. And if you plug in a value to the left of e, you actually get positive. And if you plug in a value to the right of e, you get negative. So the derivative is negative after e, which means as long as n is greater than e, f decreases. And we don't need f to be always decreasing. We just need for its end behavior to be decreasing. So as long as it decreases in the long run, we're good. And this function does. It starts out increasing, basically only its first 2 terms go up, and then it decreases in the long run. So now we're good to use the integral test. And that's exactly what we're going to do. We'll go the integral from 1 to infinity of our original function of natural log x over x dx, which is the limit as t approaches infinity of the integral from 1 to t of natural log x over x dx. All right, ideas on how to evaluate this integral? You can do a u sub. If we let u equal natural log x, then what's du? Yeah, which we have, right? 1 over x dx here. So our integral becomes just integral of u du, which is 1/2 u squared. Oh, I ran out of space. Going over here, folks. All right, which is replacing the u with ln x, I basically get 1/2. Nope, let me put my limit in there. Limit as t goes to infinity of 1/2 ln t squared. I need to evaluate that from 1 to t. And then natural log of 1 is just 0, so...
Wait, Mr. Toller.
Yeah.
With the inside bracket, the ln t that you've written down, wouldn't it be ln x, natural log x?
Yeah, oh, in the first one,
t?
yeah, I'm sorry. Yeah,
I mean, it's not that it matters too,
no, you're right.
Too much. But
Here
I know you're a stickler for that on tests.
Here it is, yeah, 100%. That would be ln x, but in the second one, I should be plugging in the t. And then if we let t approach infinity, natural log diverges. It just goes to infinity. So I can say, therefore, the series converges by the integral test. All right.